Gemstones, precious metals, and power. The building blocks of civilization. But how are they created?
Our Earth is a master chef. She knows how to cook.
It's not easy to make an element. You need temperatures that are extreme.
In this episode, how do metals shape our world?
I love steel. It's actually the backbone of our society.
And will these gifts be used to build the tools of tomorrow?
So I think of the Terminator, he can change shape and then self-heal. Actually, our material does all those things.
We're going to launch this incredible telescope, and we're going to send it 1 million miles into space from the Earth to actually unlock the secrets of the universe. And you will all rely on 2 ounces of gold.
The power of metals. Right now on Nova. By the light of an ancient campfire, a discovery was made that changed the course of history.
We don't know exactly how it happened, but I sometimes wonder whether it wasn't a complete accident.
Whether by chance or through sheer determination, once humankind learned how to harness the power of fire, we left the Stone Age behind, forging our way into the modern world with copper, bronze, iron, and steel, the metals.
A world without metals would not have tall buildings, it would not have fast vehicles, it wouldn't be able to have electricity. Really, our entire modern world is built on the backbone of metals.
Our journey begins with a metal that's transformed life on Earth through its beauty. A metal that fortune hunters were willing to die for. And not just in the movies.
There is nothing more beautiful than gold. Nothing in the world. You just feel it when you see it. Ancient people valued gold before the concept of currency or money even existed. It's something that people intrinsically knew had worth. Gold is absolutely magical. Gold is the most fantastic jewelry metal to work with. It's so soft. It's so flexible. It's like butter. Working with gold ruins you for any other metal. You're never the same again.
Jeanette, a master jeweler, is making a pair of gold earrings.
I specialize in ancient jewelry making techniques. The kind of expertise and skill that were used for making jewelry really made it an art form. I would make my own wire and sheet and practice techniques like granulation. The technique I'm going to use for the hanging fringe actually originates from Troy from about 2450 BC.
Gold is unique among the elements. Gold is extremely resistant to oxidation, to rusting. If you make an object out of gold, it's the one thing that you have that doesn't degrade. So to ancient people, it must have been very, very appealing.
The color of gold draws you in. Ancient people saw it and knew that it was something incredibly special.
Gold is not only beautiful, it's rare. In fact, if you take all the gold that's been mined to date, it's estimated it would fill about 1/3 of the Washington Monument. But to understand what makes this rare and noble metal last forever, we need to take a closer look. A much, much closer look. Using one of the most powerful electron microscopes in the world, David Mueller studies the elements.
Probably the most fun in the lab is when you put something in and the picture comes up and you look and go, well, that's not what I expected. That's interesting, and that's usually the start of a new scientific discovery.
Today, Mueller is observing the curious behavior of gold, atom by atom, All elements are made of atoms. Inside is a nucleus filled with positively charged protons along with neutrons that have no charge at all. Swirling around the nucleus in a cloud are negatively charged electrons. It's the relationship between gold's nucleus and its electrons that holds the key to its resilience.
We're now at 7,000 times magnification, 7 times higher than the highest magnification of an optical microscope. And if we zoom up some more, start to see there's this nice pattern. These little islands of gold. And if we zoom up a little bit further on them, you'll start to see little bright spots all by themselves. Those are individual atoms.
Every one of these clusters contains thousands of bright dots, thousands of gold atoms.
Little gold atoms form small clusters, and they keep rearranging and changing. They're not static, they're not stable, they're dynamic, they're moving all the time.
Gold atoms love to be together. But when it comes to bonding with other elements, they're downright antisocial. When atoms bond, they do it through their outermost electrons, by sharing or swapping them. But gold's 79 protons fight the urge, because they have an immense positive charge.
That positive charge pulls in the electrons. The real consequence is that the outermost electrons of gold are much less available for doing chemistry than we might otherwise expect.
That's why gold doesn't bond with elements like oxygen that cause metals to tarnish and rust.
The reason that we're able to appreciate the gold masterpieces from 2400 BC is because gold lasts forever. It is just as beautiful today as it was thousands of years ago. You can't say that about anything else that you could work in.
How did such a unique metal form?
It's not easy to make an element. You need temperatures that are extreme, and we're talking millions of degrees. The heavier the element, the hotter the temperatures required to make it. And you find those temperatures in the cores of stars that are 10 times the mass of the sun or greater.
It's within the intense heat and pressure of these massive cores that the elements progressively take shape, bonding together in a process called fusion.
You can sort of imagine building up all the elements that exist in the universe by taking a pile of neutrons and protons and electrons and putting them together to build up bigger and bigger and bigger atoms.
When the number of protons and electrons hit 26, forming iron, the process stops.
Once iron's made in the core, that's it. There's no more available energy for fusion. Those massive stars will explode and go what's called supernova.
One of the key open questions, though, was what about the heavier elements? What about gold and platinum and uranium? Where did those come from?
At the end of supernova explosions, new kinds of stars are formed, called neutron stars. They often come in pairs, binary stars.
They're extremely dense and compact and heavy. It weighs about 1.5 times the mass of our sun, but it's the size of a city like New York or London or Boston. And they incorporate a lot of neutrons, which is why they're called neutron stars.
Some scientists theorize that elements heavier than iron were created in the collision of two neutron stars. What happens when they collide? Fusion on a massive scale. The elements were spread throughout the cosmos, so they were in the mix when our solar system formed 4.5 billion years ago. And later, more were delivered to Earth by comets and asteroids. Most of the elements on the periodic table came to us from space. We classify them in groups defined by their characteristics. The largest group is the metals. And one of the most beautiful by far is gold. Now, This ancient treasure is going back to space. On board the most advanced telescope ever built.
It's the next big space telescope. We like to call it Hubble 2.0.
Hubble 2.0 is the James Webb Space Telescope.
2018, we're going to launch this incredible telescope, the largest space telescope mankind has ever built. And we're going to send it 1 million miles into space to stare at the earliest part of the universe. And it will all rely on 2 ounces of gold.
The ultra-thin layers of gold that coat the telescope's mirrors give it the power to detect galaxies light years away.
Hubble has sort of found the edge of the visible universe, but we know there's a whole universe beyond that at wavelength.
And that's where gold comes into the picture.
Infrared light is invisible to our eyes, but we can detect it as heat. And that's why this thermal infrared camera will pick it up. So this is my hand as viewed by the camera, and it's about 97 degrees Fahrenheit. Now, let's look at my hand reflected in this ordinary silver-coated mirror. It says that my hand is 84 degrees Fahrenheit, which is a lot less than 97. And that's because the silver-coated mirror is not a perfect reflector of infrared light. But